If you've ever sat through a mechanics lecture, you probably picture physics as an endurance exercise. You imagine a chalkboard covered in dense equations, where finding a solution means grinding through pages of raw algebra. But working physicists know that complex mechanics usually yield to a clever shift in perspective. The book 200 Puzzling Physics Problems is built on the idea that even the most daunting scenarios have an elegant core. When we learn physics, we usually deal with frictionless vacuums and isolated spheres. The calculations are clean, easy, and completely divorced from reality. As soon as we try to model a real environment, one with friction, air resistance, or changing mass, our intuition tells us the math will become an unsolvable nightmare. Decoding a messy system without drowning in equations is the true mark of mastering the subject. This standard textbook setup shows a chain on a table with portion X hanging over the edge. In a frictionless vacuum, calculating the slide time is simple. Gravity pulls that hanging weight, accelerating the chain at a predictable rate. But real tables have friction. The metal links scrape against the surface, dragging on the system. Friction typically complicates the math. As the chain falls, the amount of weight resting on the table constantly decreases. That means the sliding friction is changing every single millisecond, creating a cascading mess of variables. This graph illustrates the result of mapping that sliding time. You get an agonizingly complex set of divergent data paths. Depending on the exact coefficient of friction, represented by mu, the time it takes the chain to fall fractures into entirely different curves. Looking at a mess of data like this creates a psychological barrier. It makes us assume the physical world is just too chaotic to model elegantly. A physicist named F. Beiruzzi looked at this problem and realized there was a way out. He abandoned the brute force calculations for a coordinate transformation. Instead of fighting the friction variable, he tweaked the fundamental mathematical definitions of time and length for the system. By scaling how we measure those two properties, the friction variable gets absorbed directly into the axes themselves. Once you shift the coordinates, all of that chaotic, scattered data snaps into a single, unified curve. Here's the final result: a clean, universal function for sliding chains. Notice the axes. By plotting normalized sliding time against normalized length, this single curve dictates the exact fall time for all chains on all surfaces. The specific amount of friction no longer matters. The friction rescales the system. A single shift in perspective allows a one-page function to replace a whole volume of data. This principle applies beyond friction. Take problem 104 from the author's collection, a flexible chain moving at constant speed around two spinning cylinders, shaped like a stadium track. If the chain suddenly slips off the cylinders and falls freely, what happens to its shape? Intuition tells us that centrifugal force will take over immediately, deforming the straight edges and snapping the chain into a perfect circle, or maybe an oscillating oval. But the math reveals something surprising. The falling chain rigidly maintains its exact original pill shape as it plummets, resisting deformation entirely. The internal tension of the moving links precisely balances the centrifugal forces at every curve. That tension acts as a rigid internal frame, locking the stadium shape against the air. Once again, the physical reality turns out to be vastly cleaner and far more stable than our messy real-world intuition expects. Systems that appear chaotic, like a scraping chain or a falling loop, often harbor a very clean logic. We routinely assume that solving real-world physics problems requires heavy, frustrating mathematical lifting. But whether you are calculating the drag on a sliding chain, tracking a falling loop, or mapping an electron in a box, hitting a massive wall of algebra usually means you are looking from the wrong angle. Finding the right frame of reference allows these complex mechanics to be expressed as a single universal rule.